Hi guys, sorry for the delay. I'm working with my iPad today, and so it took a while to set this up. And so I'll be creating a new board and just like doing my work on that. And I guess I'll be switching around with the website, which has all the problems, and I guess the scratch work for my explanations. Um, Hopefully, Sid will be arriving later today, but I'll be continuing on with the our review of the 2025 MC8 with problem 20. And so this is where uh, more of our problem solving strategies will need to be used. And so I'm going to see the mirror is a little bit weird because it's showing up on both sides. Um, See if I can get rid of that. Okay, there we go. Okay, let's just start with problem 20. And if it doesn't show up, I guess I would just cover the other odd number problems. And so problem 20 reads, Sarika, Dev, Rajiv are sharing a large block of cheese. They take turns cutting half of what remains and eating it. First, Sarika eats half of the cheese, then Dev eats half of the remaining half, then Rajik eats half of what remains, and back to Sarika and so on. They stop when the cheese is too small to see. About what fraction of the original block of cheese does Sarika eat in total? Okay, now take a moment to think about that for a sec. Okay, so I know this problem is a lot of words, but I think the main idea is to actually get a feel of what's actually happening here. And so basically, we have three people, Sarika, Dev, and Rajik. And the problem says that they take turns cutting half of what remains. So basically, half of the cheese that remains, and eats that like remaining half. And so half of what remains, I guess. And so if we think about it, let's see. Okay, I know Sid that works with the pen, but the pen's a little bit janky sometimes. So let's just see how this goes. And so we have three people. Ooh, that's thick. Let's just make this smaller a little bit. Okay, now we have S, I guess. What was the other one? We have SDR. So I guess S, D, and R. And so they keep rotating, eating half of the remaining cheese. And so why is this? It's interesting because my is the board updating on your side? Okay, I think it might lag a little bit, so bear with me today. Sorry about that. So S, D, and R, and so they rotate from S, starting from S, and then just eating half of the cheese that remains. And so the problem tells us that they have a large block of cheese. And so since it doesn't really matter like how big the cheese is, we can just say like it's just 1 unit of cheese. All right. Because we actually want the total, like we want how much did S eat after like the block of cheese is too small to see. And so we want S to be we want to find the amount that S eats after this process. And so we can just say that we have one block of cheese originally, um, and we want to find the fraction of this one block of cheese that S eventually eats. And so let's see what happens after like after a few iterations of this process, because the main idea is that like you don't there's not really a good way to visualize how much cheese S actually eats in this uh, throughout this process. But like the problem basically tells us. So let's just like see what happens. Play around uh, with the process a little bit. Okay, so let's see. Um, okay, so how I would write this is that let's keep track of let's keep track of the amount that remains and see how much like they actually eat throughout the process. And so I'm gonna label this as n equals 1. So um, basically, you see why I do this. And we're gonna just create like a table like this, where S, D, and R represent like the amount of cheese that like the three people, each of the three people has eaten up till uh, the nth iteration. And so we have that. We also have, we also want to keep track of the amount. So the cheese remain. It's abbreviated like that. All right. I'm gonna draw like that, and then let's just keep going, simulating what the problem statement tells us. So I'm gonna get started at n equals 0 because we know that the cheese remaining is 1, and they haven't eaten any cheese, so it's just 0, 0, 0. How about n equals 1? Well, with n equals 1, we're going to have, well, S is going to eat half of what remains. So half of 1 is just 1. And so he's going to eat half of that, and half of the remaining cheese is going to remain, which is just a half of half. All right. And other people haven't eaten yet. N equals 2. How about n equals 2? Let's see what happens with n equals 2. Well, it's the second person's turn. It's D's turn. Let's just call him. And so S is not going to change. D is going to eat half of what remains. And so half of half is just a quarter. So we're going to, this guy's going to eat a quarter. And then quarter minus, a half minus a quarter, right, is what's going to remain because D already has eaten a quarter. And so we're going to have half minus quarter, which is just a quarter. And then, again, the third person hasn't eaten. All right, let's try n equals 3. Half quarter, because the two people are already taken a turn, but the third person hasn't. So the third person has to eat half of this, which is 1/8, right? 1/8 right here. 1/8. And half of a quarter is an eighth. And so this is what the amounts are going to look like after 3 iterations. All right. We could keep on keep on going. And let's actually do that. And I'm going to speed this process up a little bit and see, and like this, that way you'll be able to see like eventually what the answer should look like. And the answer actually looks really nice. So let's see. Let's just continue. I'm going to speed this up a little bit. All right. So S's turn. He's going to eat a half of an eighth. So I'm just going to write it as 1/2 plus 1/8 times 1/8. 1/2 plus 1/2 times 1/8. And so what's going to remain is 1/16. Other people haven't changed. N equals 5. Again, we just bring this down because it's the second person's turn. This guy's going to eat a quarter plus a half times 1/16. And you'll see why I'm writing it like that. 1/32 n equals 6. Let's just bring this down. Also, this is 1/8 right over here. Now it's the third person's turn, and he's gonna eat a total. Again, I'm storing the totals and not just what they eat on their current turn. And so the total is going to be 1/8 plus 1/32 times half, and then the remaining is going to be 1/64. Now, as I'm running out of room, but let's just do it for one more example, one more iteration. 1/2, bring everything down. 1/2 plus 1/2 times 1/8. Right, that's just the remaining. I guess like the running sum, the cumulative sum of the first person, and he has to eat half of 1/64. Okay. Now, do you see anything interesting about what happens to, I guess because we're focusing on the first person? Do you see anything about the first person total? 1/2 plus 1/2 times 1/8 and 1/2 plus 1/2 times 1/8 plus 1/2 times 1/64. Well, here it's very nice actually, because if we go back to the problem, right? Um, it says that they take turns cutting off half of what remains and eating it. And so that's interesting because when I think of a half, when I just think of the number of half and anything with twos, really, I just think of powers of two. Because what happens if we actually write these sums out in terms of powers of two, right? Let's just write it out. 1/2. Okay, it's just a half. I'm what I'm doing here is that I'm extracting out all of the different sums and then writing it in terms of powers of a half. So let's just write 1/2 as just a half, right? For this one, it's just a half plus a half, a half. Come on, the pen sometimes lags like that, and it's annoying. A half times 1/2 cubed, because 1/2 times an eighth is 1/2 times 1/2 cubed. Okay, and so for this one, it's going to be 1/2 plus 1/2, 1 times 1/2 cubed. It's going to lag again, but plus 1/2 times 1/2 to the sixth. You get the idea. Okay, so can you actually, based on this, can you make a pattern here? Do you see any patterns here? Any ideas? What we can, because we need the cheese to be like, again, like the cheese remaining, it's getting smaller and smaller and smaller as we go down. Um, but what does the expression look like when the amount of cheese remaining is virtually zero? So think about that for a sec. What should our expression for the amount that S eats be for, uh, yeah, just when the cheese is virtually zero? If you have any ideas, you can obviously drop it in the chat. But I know because there are less people here, I guess I can just explain the solution. The key idea is that if you look at the powers of 1/2, and you can see a pattern here, because we have, if we write this, we write the second sum as 1/2 plus 1/2 to the fourth, right? Because when we multiply 1/2 times 1/2 cubed, we're basically adding the exponents. There's an invisible one right here. So we're adding 1 plus 3, and the power becomes 4, right? So here, our cumulative sum is 1/2 plus 1/2 to the fourth plus 1/2 to the seventh. Okay, now notice that the powers differ by 3. So you're just increasing the power of 3 every time that you add a new power of half. And so we can conclude that our infinite sum, or what we want to evaluate, is 1/2 plus 1/2 to the quarter plus 1/2 to the seventh plus dot dot dot, all the way to infinity. So obviously the next term over here is going to be 1/2 to the 10th, because we're adding a power of 3 to 1/2 to the seventh, and then 1/2 to the 13th, all the way to infinity. All right. And so now we can evaluate this sum. And this sum is just going to be 1/2 over 1 minus 1/2 cubed. And if you're wondering where the heck did I get that from? Well, if you have a geometric series, and this is going to be a very, very useful concept in AMC 8, especially AMC 8 and 10, especially. If you have a geometric series, well, I think I'm skipping ahead a little bit, but if you have a sum in the form a plus ar plus ar squared all the way, and we also know that the absolute value of 1 is absolute value of r, excuse me, is less than 1, then the sum is just A over 1 minus R. And so we're applying this formula that you see to our problem. A is a half and R is 1/2 cubed. And so we can just simplify this a little bit. Multiply by 8 on top and bottom, we get 4 over 8 minus 1. Or, no, well, yeah. We're multiplying by 8. This, I like to write this instead of doing it in my head. You get 4 over 7. And we can just see if that's an option. That's an option, and it's option A. And just to check, because with these problems, if you have like 3 or more people, even 2 people really, you should always check if you're solving for the right person. So let's just read the problem. Last sentence says, about what fraction of the original block does Sarika eat in total? And it says that first Sarika eats half of the cheese. And so we can be sure that after doing this process, because we simulated this process for the first person being S, that we are right. And so let's just check our answer real quick. And yes, it is right. And you can see here in AOPS how they use the geometric formula. All right. If that's it joining, I did start a little bit later than expected because of the iPad issues. So I guess when the timer hits 30, I'll hand it off to you. All right. So let's move on to 22. Okay, 22, accounting problem. I see it as a accounting problem because I just see a row and the very close answer options, and that means you should be careful when we do this. All right, so here we go. A classroom has a row of 35 coat hooks. Okay, interesting. Paulina likes coats to be equally spaced, so that there is the same number of empty hooks before the first coat, after the last coat, and between every coat and the next one. Suppose there is at least one coat and at least one empty hook. How many different numbers of coats can satisfy Paulina's pattern? Okay. Now I'm thinking it's maybe not a number counting problem. It could be a number theory problem. But let's just read it one more time and we'll start. Yeah, one thing I like to do is to read the problem twice. It might, like, if you're getting close to time, it might not be possible, but if you do have time, you should definitely read the problem twice just to make sure you're not missing anything. Okay. Okay. So let's see. So the condition, usually in MCA, there's a main condition I want to focus on, so that we can just play around with the process. And so we know that there are 35 hooks. I wish I could just write on this, but I guess not. So there are 35 hooks, and the coats are equally spaced, so that there are the same number of empty hooks before the first coat. I think it's a little bit easier if I explain it with the line. So I'm just gonna like do it in the mirror. Okay, so we know that there are 35 hooks. Is that true? 35 coat hooks, yeah. So there are 35 coat hooks, right? And we know that Paulina wants the coats to be equally spaced. And so we want, let's say there's an arrangement, okay? I'm gonna say hook, H is hook, just to like make everything represent a little bit easier, and C is coat. So we want, let's just like ignore the condition that there are 35 hooks. So that's a lot of hooks, and I want to draw 35 hooks and coats. So let's just like see what the condition actually means. There's the same number of empty hooks before the first coat, after the last coat, and between every coat and the next one. Oops, sorry. So Um, yeah. So let's say there are let's say there are three hooks. All right. Or actually, let's say there are three. Mm, yeah, let's say there are three hooks. Okay. Wanna again, experimentation is really important to problem solving. Because if you don't know what's going on, you gotta like play around with the problem a little bit. Let's just see what happens with three hooks. Well, we know that according to the problem, there must be a code here, right? Because if there was a code here, there had to be a hook here. The reason being is that there are an equal number of hooks between codes, as well as before the code, before the first code, and after the first code. So we can't have an arrangement like this because you're gonna have a code without any hooks before that. So that can't work. So let's say there are three hooks. We This tells us we must have two hooks like that. All right, because if you have, I think it's a little bit easier to, again, like by our experimentation, if we have three codes, we can actually say that we can have any number of we can have x hooks in between x hooks, x hooks, and x hooks. Also, we need x hooks at the end. Because if that was not the case, right? If let's say there were like y hooks here, then the condition would be satisfied because we would have x hooks in one gap and y hooks in another gap, and that doesn't satisfy our problem condition. So we got to have x hooks, right? The same number of hooks in between, right? In these gaps between the each pair of adjacent hooks, uh, uh, coats, and we also got to have x hooks like before the first and after the last. And so that's so we can actually say that if we have y coats, actually here, okay, let's just play with this one first. I don't want to make it too general. There are three coats, right? There are three coats. And how many gaps are there? How many gaps of hooks are there? That's a good question to ask. Well, we see that there are four gaps, right? We have one gap here, second gap here, third gap here, fourth gap here. So there are four gaps. So four gaps, and then each with having x hooks. So how many coats and hooks? But remember, we can't have a coat on a hook. Technically, you can, but like according to this problem, you can't have coats and hooks like all on one. So C and H's are different. So how many total are how many total objects, coats or hooks are there? Well, since there are three coats and there are four gaps, each having x hooks, we get that there are 3 plus 4 times x, or 3 plus 4x amount of objects. All right. And x can be any number, right? Well, it can't be a you have to be careful because the problem says that there is at least one code and at least one empty hook. So you can't have x can't be 0, and the number of codes can't be 0. So we can't have x equals 0. X equals 0 here. All right. So that's nice. All right. That's nice. This is the number of hooks and codes. Okay. Now let's generalize and refer to our experimentation as a guide. Let's say there are y hooks now. And again, this problem is the exact same, except that I'm using a variable for the number of hooks. So let's say there are y hooks. I'm going to draw a line like that. C, 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 dot, 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 C. Let's say there are Y hooks. Oh, sorry, Y codes, I mean to say. Just quickly erase that. Y codes. Okay. How many gaps are there? That's the key question. How many gaps are there? Well, if we had 3 codes, we had 4 gaps. What if we had, because we only tried one, we don't know if there's a pattern for other ones. Let's say they have 4 codes. How many gaps are there? Well, if you draw a line of 4 codes like that, there are obviously 5 gaps. So if you have, okay, let's just write it down. If you have 5 codes, you're gonna have, oh my god, this is 4. If you have 4 codes, you're gonna get 5 gaps. So if you have Y codes, it logically makes sense that you have Y plus 1 gaps. And again, using the same general argument here, we can assume that there are X hooks in between everything. So X hooks in each gap. So how many objects in terms of X and Y are there? Well, we know that each gap has X hooks. So again, we can use this problem to solve, to basically actually solve for the problem. Okay, we get, so the total number of things, codes or hooks, is Y plus 1 times X. And we know that equals 35, right? 35. Yeah, 35 hooks. And I guess if you read this problem again, it does say that Paulina puts the coat on the hook. But again, if a coat is on a hook, why would you need to say that there's a C and an H right on top of each other? We just say that if a hook is occupied, we can just denote that as C. It just makes life a lot easier. So y plus 1 times X equals 35. And so we want the number of order pairs, the problem translates as this: the number of order pairs of integers x, y, such that x is at least 1 and y is at least 1. All right, so now we can just do a little bit of rearranging. X, distribute first. X, y times x is xy. 1 times x is x. And then you just carry this over, and that's 35. Ooh, this is a very nice form because this is a little bit more of a more advanced technique. But if you add 1 on both sides, you're going to get xy plus x plus y plus 1 is 36. 35 plus 1 is 36. And now you can look at what happens. If you factor out x from the first 2 terms, you get x times y plus 1. And then if you just factor out 1, we'll just leave it like that. You get y plus 1. And right hand side is 36. Now you can actually factor this even further as x plus 1 times y plus 1 equals 36. How nice. And so the reason why this is nice is that we want the number of x, y such that this is true, as well as the condition that x and y are both at least 1. So we got to be really careful that we do that. And so how I resolve this condition, this annoying condition, is that I add 1. And that gives us x plus y is at least 2, because x is at least 1 implies that. And similarly, y plus 1 is at least 2. And so let's just iterate through the number of ordered pairs, such that let's just call these 2 quantities x prime and y prime. Just rewrite it at that. Now we can see that our conditions are that these x prime and y prime are at least 2. And so we can just list out the order factors as follows. x x prime can't be 1, has to be at least 2. And so when x prime is true, y prime is 18 because they have to multiply by 236. When x prime is 3, y prime is 12. X prime is 4, y prime is 9. X prime can be 5, 36 is not divisible by 5, and you get 6 and 6. And you can just reverse it because if once you hit something like that where the divisors are equal, you can just reverse these pairs. And so get 9, 4, 9, 4, 12, 3, 9, 2, or 18, 2. My bad, 18, 2. So how many pairs of integers is that? Well, you get 1, 2, 3, 4, 5, 6, 7. So the answer is 7. Is that an answer? Yes, that's an answer. Okay, let's check if this is right. Hopefully this is right. Yes, that is right. And you can't forget, again, you got to be careful because it does, and this is why it's really good to reread the problem. It says that there's at least one code and at least one empty hook. So you got to be careful that when we do something like this, oh, by the way, this is called Simon's favorite factoring trick. So it's called SFFT for short. So you can just search that up if you're wondering like how like what's the intuition behind this. You just got to be careful. Again, got to be careful that x and y are at least 1. That leads to this. And again, if you're performing a substitution, you must not forget this condition right over here. That's the tricky part. Otherwise, again, it's just this problem is about recasting like a seemingly like sophisticated problem in terms of like variables, and then reformulating the problem as we did over here, like finding number of ordered pairs instead of finding number of arrangements. And we got that from experimentation. So experimentation is really powerful. Definitely do that when you're stuck. Yep. If Sid's on, then I'm gonna hand it over to him. I know I went a little bit over. So thank you
Yeah,
guys.
that's fine.
Yeah, and he'll be continuing with the odd number problems. So see y'all later.
Yeah.
I'm gonna close this all. Close this. Um, yeah, stop sharing. All right, thank you guys. And if you have any questions, just like drop them in chat.
Yeah. All right, guys. So, as usual, I'll be covering the odd number problems. I believe there are only two that are left because I covered 23 last time. It was the Konigsberg School problem. And so there's two problems left, 23 and 25, right? So let's go through 23 first. 23 says how many four digit numbers have all three of the following properties? Okay, my bad. So the following properties. So the tens and ones digit are both nines. So okay. So if I have a four-digit number, say I don't know ABCD, right? The tens and ones digit are both nine. Okay, so our number is gonna look something like AB99. All right. Our number is also one less than a perfect square. All right. So let's say the perfect square is P, right? The number is going to be one less than a perfect square. So I guess P minus one. But what can be really useful, if you think about it, is P has to be the square of some number, right? Because it's a perfect square. So like for example, I could say 25 is a perfect square, and then we want a number that's one less than 25, right? But we got to remember that 25 is a perfect square, so it's like some number x squared, right? So we can just look at those numbers instead of looking at numbers p minus 1, because that really doesn't give us anything. Rather, x squared minus 1 might lead to some factorizations that might be useful for us. So instead of analyzing p, how about we analyze, so we're going to say p equals x squared, and so we'll analyze all the numbers of the form x squared minus 1, right? So this could be like 5 equals 25 equals 5 squared, x is 5, and p is 25. So I'll just write that just in case it's ambiguous. right? So something like that. Um, and then it also says that the number is the product of exactly two prime numbers. All right. So let's analyze statements one and two in the beginning, right? So it says that the tens and ones digit are both nine. So that means that our number is in the form AB99, right? But we got to remember that any number that ends in 99 will be like the number that's one greater than that will be some number, let's say C0, or let's say um so let's say something like this, CD00, right? You look at I don't know, you look at let's say 2500. The one less than that is 2499, right? Like and then obviously uh b is uh b is d minus 1, right? Because if you add 1 to this number, you'll definitely get some number in the form of uh get some number that has two ending digits of 0 at the end, right? So we just have to look at those. I guess then we just have to look at those numbers that yield ending digits of 0 and are perfect squares, right? Because we got to remember that. So let's say x equals 5, p equals 25. We got to remember that condition that says the number is one less than a perfect square, right? So let's look at numbers. So I guess we just have to look at numbers that are uh, ending in, I guess, ending in two zeros. So like a multiple of 100, right? So every number, I'm just gonna keep that on here. Every number that's a multiple of 100, right? Uh, is we're gonna look at those numbers, right? Because one less than that uh, satisfied satisfies both conditions one and two. Does that make sense to you guys? If it doesn't, just drop questions in the chat, and I guess Daniel will address them. Right. So we're just looking at multiples of 100 now, because then we'll just subtract one off that, and that's going to satisfy one and two. No other number minus one is going to yield uh, a number or a four-digit number where both the tens and one digits are nine. Well, yeah, sure, it can uh lead lead to a ones digit of nine or a tens digit of nine, but for both to be nine, you need it to be a multiple of 100, right? That's just basic arithmetic. So I guess we'll start from uh well, let's see. Okay, so does 30 squared work? No, right? Because 30 squared is 900, and the 900 minus 1 is not a four digit number. Does 40 squared work? Yeah, because 40 squared is going to be 40 squared minus 1, because remember it says we have to find a perfect square. So let's say x equals 40. X squared minus 1 is going to be some four-digit number, 1599, right? Something like that. Will 50 squared work? Well, look at these two numbers. Yeah, so look at these two numbers. I guess I just unknowingly wrote it, but I guess these two numbers both, I guess this number satisfies, or the bottom number satisfies both conditions one and two, which is that it's one less than a perfect square, 2500, which is 50 squared. And then the tens and ones digit are both 9, 499, right? So that's 2499. Or we can keep going on until what number? What's the maximum number for which we can get a four digit number when we subtract one off it and have both the ending digits in 99? Well, first of all, we got to remember that if you want to get a multiple of 100, which is a perfect square, the so if you want to get, say, p, or yeah, so if you want to get p as being a multiple of 100, x must be a multiple of 10, right? That's just generally true, because um, x must be a multiple of 10, and it can't be a multiple of anything else, because if you get like 10 times a positive integer, say n. If you're squaring that, you'll get n to be some two digit perfect square integer, right? And then times 100, which is always going to have two trailing zeros at the end. So the maximum number that we're looking at is 90, because if you're looking at 100 squared, 100 squared minus 1, actually, does that work? Yeah, I think 100 squared also works, because uh so 90 squared minus 1, and then 100 squared is 10,000, right? So I'll just write that 100 squared is 10,000, but that minus 1 is 9999, and then this is whatever, right? But now we just gotta see how many of these. So now we gotta take care of number 3, which says the number is the product of exactly two prime numbers. Well, we got to remember that we can use difference of squares. This is why I told you guys to write these numbers in this form, because uh, we can actually use difference of squares to break down numbers prime factorization. So this number 40 squared minus 1, or 40 squared minus 1 squared, right? So a squared minus b squared is a plus b times a minus b. So 40 squared minus 1 squared is going to be 41 times 40 minus 1, which is 39. Is that the product of exactly two prime numbers? No, because 39 is not prime. Well, let's look at 50 squared minus 1. 50 squared minus 1. Okay, 50 squared minus 1, since I wrote the number down, you guys can clearly see that it's not a multiple a prime, or, well, let's look at the prime factorizations, right? So it's going to be um, 50 squared minus 1 squared. So it's going to be 50 plus 1 times 50 minus 1, which is 51 times 49. Again, clearly not the product of exactly two prime numbers, right? Now let's look at 60 squared minus 1, because we're going to look at 60, 70, and then 80. So let's look at 60 squared minus 1. 60 squared minus 1 is going to give us 60 squared minus 1 squared, which is 60 plus 1 times 60 minus 1. 60 plus 1 gives us 61, and 60 minus 1 gives us 59. Well, this works because 61 and 59 are both prime, right? That's what it says. If exactly two prime numbers, this works. How about we look at 70 now? Well, okay, so 70 squared minus 1 squared is going to give us 70 plus 1, which is 71, and then 70 minus 1, which is going to give us 69. Well, 69 is not a prime number. It's divisible by 3 and 23. So that's off. And then 80 squared minus 1 is going to give us 81, 80 plus 1, and then 80 minus 1, which is 79, right? So 81 times 79. Is 81 prime? No, right? So this is definitely not a viable number either. How would we look at 90 squared minus 1? 90 squared minus 1 is going to give us 90 squared minus 1 squared. So it's going to give us 91, 90 plus 1, and then 90 minus 1, which is 89. And then similarly going on, this is also not a viable case, because 91 is definitely not a prime number. It's divisible by 3 and or 13 and 7. And then last but not least, let's look at 100 squared minus 1. 100 squared minus 1 is going to give you 101 times the 99. Again, 99 is not a viable case again, because 99, or 101 times 99 is not a viable case, because 99 is not a prime number. It's divisible by both 9 and 11. So the only answer that works from all of our possible options from statements 1 and 2, that also satisfies statement 3, is 61 times 59. So it's only one integer. That, or how many four-digit numbers? It's only 60 squared minus 1 that works. So our answer here is B, 1. Does that make sense to you guys? If not, please drop questions in the chat, and Daniel will answer them. Um, but yeah, if okay, cool. Um, so yeah, um, let's move on, because I think we're running a bit short on time. But if you guys notice, this problem was a lot easier than the other problem, which was the Konigsberg problem, and I believe that just because the problems ranked higher or problems numbered higher than another problem. So the other problem was number 21. If you guys remember the conic square problem with the different graphs and stuff. But this is 23. But this one I think is definitely significantly easier because it just required. It's not significantly easier, I guess, but it's a bit easier, right? Because you just had to notice one or two things, and this problem would work out perfectly, right? So I guess just a strategy or and practice of solving problems or looking at every single problem on the test and like not being afraid to try harder problems because a lot of times they become easier problems than some of the problems before that, right? So don't be afraid to skip around the test and jump around and see what works for you. So now we move on to the penultimate problem of the test, problem 25. Problem 25 says Michaela finds all the possible ways to draw a path in a 5 times 5 diamond shaped grid. Each path starts at the bottom of the grid and ends at the top, always moving one unit northeast or northwest, right? So she starts from here, she ends up here, and she always makes a series of paths, and that's how she gets there. She then computes the area of the region between each path and the right side of the grid. So I guess this is the right side of the grid, right? So she computes the area, say, of this region right here, and it says that it's a hmm. Yeah. So it says that this is a 5 times 5 diamond shaped grid, right? So each square is like one unit, right? So actually, let's compute the area of one of the examples. You see how this is given as area equals 13? Well, why is that? So if you look at the square more closely, between the right side of the grid, right, and the area is just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's just the number of squares, right? So that's how you get the area of I guess the path that's desirable that she wants, right? And similarly, if you count the the number of squares in this shape, you'll get 11, right? So that's how she's computing the area of the region between each path and the right side of the grid. That's their computation technique, right? Okay, so now that we have that out of the way, it says what is the sum of the areas determined by all possible paths? Okay, so let's draw the grid, right? So one, two, three, four, and then one, two, three, four, right? So she starts, I'll use a different color. She starts from here, she ends up here, right? So there's two different, I guess, two different components to the final answer, which is the what is the sum of the areas. We want, first of all, we want the number of, uh, yeah, the number of paths that she can use, right, to get to the top, right? Because that's important. That's what's gonna get us to, I guess, the sum of the. If you want to find the sum of the areas, we first got to find out how many of those possible paths even exist, right? So, in order to do that, so number of possible paths, and to find the number of possible paths that get her from, say, I guess, point A to point B, which is from one side of the square to the other side, we gotta see um how what in what order she makes the steps. So it says that she makes the steps one unit northeast or northwest, right? So like you could argue that, yeah, you could look at this diagonal square and think about like the number or northeast or northwest, but I just decided to rotate the square so that it's facing us straight. And so she either goes uh yeah, she either goes up or to the right. Here she goes northeast or northwest. So like right here, if you guys know the cardinal directions, so this is north, this is south, this is east, and this is west. So she goes either northeast or northwest. So like she's going either northeast, something like that, or northwest, something like that, and the northeast, and the northwest, and the northeast, right? But I'm just gonna place it straight so that it's much easier for us to visualize. Well, to get from point A to point B, how many right turns does she have to take? So she has to go one right, two right, three right, four right, five right. So she has to take five right turns. And how many steps up must she go to reach B? Five ups, right? So one, two, three, four, five, right? Now here's the most important part of the problem. It's we if you want to calculate the possible path uh such that she gets from point A to point B, you have to look at the number of possible ways or the number of distinct ways to organize this word. And the word is any path that she travels in this grid is gonna consist of five rights and five ups. That's invariable. That's any path. You can go through a bunch of different paths in your. If you guys have time, you can experiment through a bunch of different paths, and you find that no matter which order there is, yeah, it could be that they're not all straight R. It could be that there's RRU, something like that, but there's invariably going to be five rights and five ups. So we just have to find the number of distinct ways that we can organize this 10 letter word, and we're done. Well, think about how to organize this word. Uh, you have um, 10 words, so there is 10 factorial ways of organizing them in total. Because, say, for this you have 10 ways of placing, so you have 4, 5, 6, 7, 8, 9, 10. Say you have the first U. First U has 10 possible options for which it could go, right? So let's say it goes here. Second U has 9 different options. So it goes U. So it goes here. And similarly, it goes 10 times 9 times 8. And we multiply because these events are independent. Placing this U has no effect on where this U goes, right? So, oh yeah, yeah. And so this is 10 factorial. But wait, we have to divide, we're overcounting because there's 5 R's and there's 5 U's, right? So, for example, let's look at uh, or I guess I'll just tell you guys what it is or how to mess up the overcount, but you guys should definitely learn this technique or learn how to do this in your own time, right? But due to a shortage of time, I'm just gonna go through it. Um, so if there's 5 R's, we gotta divide 10 factorial by 5 factorial because this way of placing 10 letters is assuming that every single letter in the word. So let's say this is a 10-letter word. Every single letter in the word had to be distinct in order for this to happen. But since that's clearly not the case, there is going to be some cases that we are overlapping. Uh, for example, if we were to make U's distinct, we would have say U1, U2, U3, U4, U5. And if you had R1, R2, R3, R4, R5, then it would be 10 factorial. But since we know that's clearly not true in an alphabet, if you place 5 U's in a row, it's the same thing, right? That's the same thing as placing um, so say U2, U3, U4, U1, U5 is the same thing as U1, U2, U3, U4, U5, right? That's how you'd get 10 factorial. This is how you'd get 10 factorial, but we're clearly not doing that because, well, a U is a U, right? Like in an alphabet, a U is a U. Doesn't matter if it's U1, U2, it's just a U, right? So that's why we're dividing by 5 factorial here. And similarly for the R's, we got to do the same thing because we don't care about R1, R2, R3, R4, R5. So times 5 factorial. And when you do this, I believe you get 10 times 9 times 8. So I'm just reading through the calculations a bit, but you guys should definitely do this in your own time and see if it works out. So it's going to be like, yeah. So 9 times 4 times 7, which is 252. So there's 252 possible paths. Uh, yeah, 252 possible paths. But now we're not done yet, right? Because the problem literally says, what is the sum of the areas determined by all the possible paths? Well, for now, there is another trick, right? Say you say this is the path that the guy takes, right? Um, so this is the path that the guy takes. What's the area of the path? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So area equals 13, right? Yeah. So uh, yeah, because we remember we said that the area is just determined by the number of squares here. So there's 13 squares in its path in the path that he goes through. So A equals 13. Well, what you got to notice is that in this 252 possible paths, right? Uh, in this 252 possible paths, you notice that if there is area equals 13, then there's so let's say this is the path that works. So we're gonna determine two different areas. A1, which is, say, I guess in this case 13, and A2, which is 25 minus 13, which is 12. So this is 12, right? If A1 is 13, then the other squares that remain is 25 minus the number of squares that work, right? So if in this case the A1's what worked and A1 is 13, then the number of squares that didn't work, I guess, or wasn't a possible combination, was 25 minus 13, which is 12, right? So 12 squares remain, and those 12 squares didn't work, I guess, right? They weren't a possible path, right? Uh, so uh, so there's A1 and A2, right? And so these two together make up 25, an area of 25, so 25 different squares. So we could actually use a trick here. We can say that since there's 252 possible paths, we can say, so I guess instead of thinking about the number of paths being just A1, right? Because A1's what works. A1's what always works. A1's like the correct path. We can think about the number of paths being A1 plus A2. And if we think about that, A1 plus A2, right? Then what's the sum of the areas determined by all possible paths? Well, now we say that from number of all possible paths, which is correct, right? This is A1. But now we're saying that number of all possible paths is A1 plus A2. Like the area of all possible paths, just A1, we are just saying that it's A1 plus A2, right? Which is going to give us 25. So now we say that 252 times 25 is our answer. But wait a second, is that the actual answer? No, because that will be the answer if A1 plus A2 equals 25, and that was the only part, and those were the possible paths that counted. But we know that that's clearly not true. A1 is the only possible path that counts. A2 is just some rubbish, right? But what you got to realize is that A1 and the number of paths that have A1 and the number of paths that have A2, symmetrically, those numbers must be the same, right? Because if you have now a path of, say, area A1, you must always have a path of area 25 minus A1, which is going to be 2, right? So since we overcounted by 2, we got to divide by 2.